In this video, we'll see how to synthesize alcohols using Grignard reagents. So first we have to learn how to make a Grignard reagent. So you start with an alkyl halide, so over here on the left, and you add magnesium metal. And you need to add something like diethyl ether as your solvent. You can't have any water present because water will react with the Grignard reagent. And so this is what you make over here on the right. You end up with a carbon atom bonded to a metal, right? So carbon is bonded to magnesium. This is called an organometallic bond. And you can do this with other metals. You can do this with lithium, for example. But Grignard reagents are one of those things that's always talked about in undergraduate organic chemistry classes. And you can see that these two electrons here, these red ones, the ones in red, I've drawn it like a covalent bond, the bond between carbon and magnesium. But in reality, it's more ionic than covalent, so it's equivalent to the second structure down here. Now, in terms of electronegativities, carbon is actually more electronegative than magnesium. So the two electrons in red are actually going to be closer to the carbon atom itself, giving the carbon a negative charge and forming a carb anion. So this is a carb anion that is formed. And this is unique because this carb anion can now act as a nucleophile in your mechanism to make alcohols. So this is the preparation of a Grignard reagent. It's proved to be a very, very useful thing in organic synthesis, so much so that Victor Grignard won the Nobel Prize for his research into this chemistry. Let's take a look at the mechanism to form a Grignard reagent. So I'm going to start with my alkyl halide, and this time I'll draw in all of my lone pairs on my halogen, like that. And we're going to add magnesium, right, which we know, being in group 2, magnesium has 2 valence electrons. I'm going to draw magnesium's 2 valence electrons like that. In the first step of the mechanism, magnesium is going to donate one of its electrons, right? So we're going to show the movement of one of its electrons over here to this carbon. We're going to use a half-headed arrow like that. So we're going to make a new anion here because this carbon actually picks up an electron, so it actually picks up a negative charge. And we call this an anion radical. Okay, so this intermediate here is called an anion radical. So I'll go ahead and write that. So it's an anion radical. It's an anion because it picked up an electron, giving it a negative charge, and it's a radical because that electron is unpaired. So this anion radical is unstable and it's going to fragment. So these 2 electrons right here are going to come off onto the halogen. Right, so let's go ahead and draw what that would give us. We now have this carbon with 1 electron around it on the right side like that. And now our halogen over here, right, it had 3 lone pairs. It just picked up another, so it is now negatively charged like that. And the magnesium that we started with donated an electron. Right, so this magnesium has 1 electron left around it, 1 valence electron, and it donated an electron, which gives it a +1 charge. Right, so this magnesium is now positively charged because it donated an electron in the first step. And in the next step of the mechanism, magnesium can donate its second valence electron. And it's stable for it to do so because then it'll have an electron configuration like a noble gas. So magnesium is going to go ahead and donate its second electron over here to the carbon like that. And let's go ahead and draw what would result. Okay, so we're going to now have our carbon right here with 3 bonds with now 2 electrons around it, and that's what gives it its -1 formal charge to make a carb anion. Magnesium has donated both of its electrons, so this magnesium is now a +2 charged cation, right? So Mg2+ like that. And then the halogen is going to form an ionic bond with the magnesium on the right side here. So we have our halogen, which is negatively charged, right? So we have a magnesium with 2 positive charges, and then we have 2 things with negative charges around it, forming ionic bonds, right? So this is our carb anion, and so I could redraw the stuff on the left with this carbon here. I can make it an R group with a lone pair of electrons, a -1 formal charge, and all the stuff on the right I could just write it like this. There are several ways that you'll see this written. I could just say this is Mgx with a +1 charge. So this just allows us to focus in on this carb anion here with a -1 charge. Or I could just pretend like everything's covalent and just save myself some time, right? I could go like that, and organic chemists understand what this organometallic compound means, that the R group is negatively charged as a carb carb anion. So you'll see several different ways to write a Grignard reagent, just as long as you understand what's going on. That's the most important thing. So let's now take the Grignard reagent we just formed and let's make an alcohol with it. Okay, so I'll go ahead and write it the last way I did. Doesn't really matter how you do it. All right, so this is our generic reaction. We're going to introduce a carbonyl compound. So for this generic reaction, I'm just going to say it's some generic carbonyl. So I'm not going to show what's attached to either side of my carbonyl carbon here. And diethyl ether, once again, is our solvent. You have to exclude water from this reaction again because the Grignard reagent will react with it. So in the first step, you want it to react with your carbonyl. In the second step, once it's reacted with its carbonyl, it's okay to add water in the form of H3O+, and this is going to form our alcohol. So we're going to form an alcohol as our product. And this carbon here came from our carbonyl, and this R group is going to attach to that carbonyl carbon. That comes from our Grignard reagent. So it's a very useful reaction because it's a carbon-carbon bond-forming reaction, right? So this R group had a carbon on the end, and then this carbon right here. So forming carbon-carbon bonds is very important when you're trying to build large organic molecules using synthesis. So this is a very useful way to form either a primary, secondary, or a tertiary alcohol. It all depends on what sort of carbonyl compound that you're starting with. So let's show the mechanism for what's happening. All right, so I'm going to say the Grignard reagent is a source of carb anions. Right, so I'm just going to draw my carb anion here like that, and then my carbonyl. Right, I have carbon double bonded to an oxygen. And I'm going to make this, anything could be attached to the carbon for right now. Once again, when you're looking at carbonyl chemistry, all you have to do is think about electronegativity differences between carbon and oxygen, right? So go back and watch the electronegativity video. We know that oxygen being more electronegative will draw these electrons in this double bond closer to it, giving it a partial negative charge, leaving our carbon partially positive, right? So carbon being partially positive, carbon wants electrons, right? Carbon is an electrophile. And from our Grignard reagent, we have a nucleophile. The carb anion is going to act as a nucleophile. The negative charge is attracted to the positive charge. So the carb anion attacks the carbonyl carbon like that, which would kick these electrons off onto our oxygen. And we'll go ahead and draw the intermediate here. So we now have our R group directly attached to our what used to be our carbonyl carbon, and now our oxygen has 3 lone pairs of electrons around it, which give our oxygen a -1 formal charge like that. So that's the first step of our reaction. In the second step, we have hydronium ions floating around, right? So H3O+. So we'll go ahead and draw H3O+ here, like that. And the second step, of course, will be acid-base chemistry. Right? So lone pair of electrons on our oxygen takes a proton from H3O+, leaving these electrons behind to form water, and that is how we get our alcohol. Okay, so that's going to give us our alcohol as our product. So after our acid-base reaction. All right, let's look at 3 different examples of synthesis of alcohols. Okay, and let's show the different types of alcohols that can be produced. So we'll start with formaldehyde here. So we'll start with a very simple molecule like that, and we'll go ahead and already make our Grignard reagent, and we're going to make methyl magnesium bromide. So methyl magnesium bromide we're going to add in our first step. We're going to use ether as our solvent, and in our second step we're going to add H3O+. Now, when you're analyzing a Grignard reagent, you pretty much have to think, where's my carb anion, right? So this carbon right here is negatively charged. That's the carbon that's going to attack my carbonyl. So if this carbon attacks my carbonyl, right, and the electrons kick off onto here, right, as our intermediate, we would have hydrogens on either side of our carbon, a negatively charged oxygen up here, and the R group this time is a methyl group like that. So after you protonate it, right, in the second step, so after these, so we'll just say these lone pair of electrons are going to pick up a proton from H2O+, right? We would form this carbon with 2 hydrogens. We're going to protonate our alkoxide to form an alcohol up here for our product. And if you look at that molecule closely, you'll notice it is ethanol, right? So you make primary alcohols if you use formaldehyde. All right, so this is a primary alcohol. Right? It's primary because the carbon attached to the OH is attached to one other carbon. Let's see how we can make secondary alcohols. Okay, so this time you need to start with an aldehyde. So instead of two hydrogens on either side of your carbon, as we did before, this time you have to have an R group on one side. So this will be our aldehyde, like that. All right, and let's go ahead and use the same Grignard reagent. We'll use methyl magnesium bromide again, like that. And second step, H3O plus. So once again, think about what is your nucleophile, right? So the negatively charged carbon is going to be my nucleophile. It's going to attack my carbonyl, kick these electrons off. So once again, when we draw the intermediate, right, up at the top here, we have our alkoxide anion, negatively charged. The hydrogen is still there, and what we did was we added a methyl group on. So this CH3 at the bottom of our intermediate came from our Grignard reagent. And once again, acid-base chemistry to protonate the alkoxide will form our secondary alcohol, like that. So that would be the secondary alcohol that is produced from this reaction. Once again, this carbon is attached to two other carbons, making this a secondary alcohol. All right, so one more example here. This time we will react our Grignard reagent with a ketone. All right, so we'll start with our ketone over here on the left. So here's our ketone. So it's cyclohexanone, and once again, let's stick with methyl magnesium bromide. All right, so we have methyl magnesium bromide that we add, and again, our solvent is ether, excluding water. And second step, we're going to add a source of protons, so H3O plus. So once again, exact same mechanism, exact same thinking involved, right? Our negatively charged carb anion attacks our carbonyl carbon, kicking these electrons off onto our oxygen, right? So we form our intermediate. Right, so this top oxygen here now has three lone pairs of electrons, negatively charged, and actually, let me go ahead and take that off there, so we can better show the atoms attached to that carbonyl carbon. Right, so if I'm showing that methyl group attacking that carbonyl, I'm going to push the alkoxide over here a little bit to the left, and that's going to get my negative charge. And that way, that just gives me some space to put my methyl group right here, like that. And that just looks a little bit closer to what my final product will look like, right? So this lone pair of electrons, right, as usual, right, this lone pair, one of these lone pairs is going to pick up a proton right here, and that's going to form our product, right? So we now protonate our alkoxide to form our alcohol, like that. So our alcohol is going to form right here, and then our methyl group adds on right here. And if you look closely, you can see this is a tertiary alcohol that we just made, right? So this carbon is connected to 1, 2, 3 other carbons. So Grignard reagents are very useful for making alcohols, and you can make either primary, secondary, or tertiary alcohols from them. So it's a very versatile reagent to use. In the next video, we'll take a look at more about Grignard reagents, and we'll talk a little bit about how to work backwards and think about synthesis problems.